Kia ora Year 12. This video is because lots of you are going to be away on your Duke of Ed tramp yesterday, so I'm just going to video about 3 different ones looking at the questions we're going to do in class. And this first one is pretty easy. It's about the difference of 2 squares, but then the new pattern that we get with complex numbers, which is the sum of 2 squares. So there's no question to work through. I'm just going to talk and you can just take notes as I go. So remember way back when we started doing algebra back in year 9 or 10, we saw the difference of 2 squares pattern over and over. And it comes up all the time. It comes up in lots of really difficult problems. It comes up in scholarship questions. And if you spot it, it almost always makes your life easier. So very quickly, can you just pause the video and factorize each of those? Make sure that you've got the pattern in your head. Okay, so the basic one, x squared minus 1 is x plus 3, x minus 3. The next one's going to be 3y minus 8x or plus 8x, 3y minus 8x. So I'm looking here at the number and I'm looking at the letters. This one, x to the power of 8 minus y to the power of 6. So I'm going to halve the power here. I'll have x to the power of 4, x to the power of 4 plus y cubed minus y cubed. So just checking quickly that that one works, we get x to the power of 8 here, and then we add this y cubed x to the power of 4, and we subtract the same thing. And lastly, we subtract y to the power of 6. So that's all good. But I want now to look at the new pattern that we get with complex numbers. And this is one of those things that it's worth drawing out. You'll notice it as you go, but it's good to start to spot it as a particular pattern type. So going the other way, let's start with z take away 3i times z plus 3i. So the pattern we get now is going to be z squared minus 3iz plus 3iz. And then we get minus 9i squared, which gives me z squared, this goes, plus 9. So suddenly, instead of having a difference of 2 squares, it's pretty cool because we've got a pattern for the sum of 2 squares. So where this comes in handy is that we can factorize if we see something like this, z squared plus 16. We can think of that straight away as z minus 4i times z plus 4i. Make sure your z's look more like z's than mine. Another one, just to practice, try that one, 4z squared plus 81. So until now, when you've seen that, when we were just working with real numbers, the answer was, oh, we can't factorize that. But actually we can. We can factorize it using the sum of 2 squares and imaginary numbers pattern. So that one will be 2z plus 9i times 2z minus 9i. Now that brings me on to solving quadratics and higher order polynomials. So we're just going to blast through 2 ways to solve or to think about this question. So suppose we're asked to solve z squared plus 4z plus 13 equals 0. I want you to do this question twice. The first time I want you to do it using the quadratic formula, and the second time I want you to do it using completing the square. This is especially for Andrew. But in this case, I think you're probably going to go, oh, the quadratic formula is much better. But sometimes completing the square is a nice thing to help you get into a problem. So pause the video and do those 2 things. Right, so using the quadratic formula, first we've got a is 1, b is 4, and c is 13. Now, we should already be thinking that this is either going to have real roots or it might have complex roots. Because the coefficients are real, we know that if it does have complex roots, one is going to be the conjugate of the other. Because the conjugate root theorem tells us that the roots appear in conjugate pairs as long as I don't have complex coefficients. Right, so we get z equals negative 4 plus or minus the square root of b squared, so 16 minus 4 times 1 times 13 divided by 2a. Giving me z is equal to negative 2 plus or minus 1/2 times the square root of 16 minus 52, which is negative 36. So z is equal to negative 2 plus or minus 1/2 times the square root of 36 times the square root of negative 1, which gives me z equals negative 2 plus or minus 1/2 times 6i. So z equals negative 2 plus or minus 3i. So you can see the conjugate pair thing happening there. We've got z equals negative 2 plus 3i and z equals negative 2 minus 3i. Now, just as a little bit of extra practice while we're in this question, let's think about where they sit in an Argand diagram. So it's going to be a very badly drawn one. Here's -2. So this is the real axis. This is the imaginary axis, mz and rez. -2 plus 3i. We'll call this one z1, and we'll call this one z2. So look, you can see the conjugate pair thing happening. This is down at -3i, and this is up at +3i. We could go on from there. In fact, we will, and we'll get the magnitude of those two numbers just for some practice. No reason to do that, except that I said. So the magnitude of z1 will be -2 squared plus 3 squared. Remember, the magnitude is the length of the line from the origin to the point. So that's the square root of 13. All right, now, but what I asked you to do was to also do it by completing the square. So let's do that now. This is going to feel less comfortable than doing it with the quadratic formula. But we're going to see what happens. So we get z plus 2 squared minus the 4 that I've added in by mistake, right? So I'm halving the 4 to get the 2, but I've accidentally added in 2 squared, so we take it out, plus 13 equals 0. So z plus 2 squared plus 9 is equal to 0. So when I've written it like this, you can see that I've got the sum of 2 squares pattern. So we can go straight to this. Sum of 2 squares, well, it's going to be the first one, z plus 2, chuck that in each bracket. So if it's plus 9, it's going to be plus 3i here, minus 3i here. And that lets me read off straight away, z equals -2 plus 3i, or z equals -2 minus 3i. So we get our two roots, z1 is equal to -2 minus 3i, and z2 is equal to -2 plus 3i. So there you go, two different ways to think about the same problem. Quadratic formula is really good, but it is really useful to have other approaches that we can take. And in this case, the thing I want you to get into your brains is the sum of 2 squares patterns. Thanks for watching, and I'll do a couple more videos this afternoon with some harder problems that we're going to look at tomorrow.